Exam 1 correction. Problem 2. A block of mass M is connected to two springs. Each spring has a relaxed length L0. The spring on the left has a stiffness Ks, while the spring on the right has a stiffness 2Ks. As shown in the diagram, the block is initially released from rest at x equals L0 over 3. The bottom surface supporting the block is frictionless. So the main concept is spring force in this problem, which is F spring equals negative Ks S. Ks is the spring constant, which is in Newton per meter, while S is in meters, which is the displacement of the spring when it's at rest minus the spring when it's stretched out. And it's the absolute value of that. Part A. Choose the block as a system and use the usual axis system with the plus x to the right and the plus y running vertically up. Just after you release the block, which external objects are interacting with the chosen system? So in this system, there's the left spring, the right spring, the earth, which is G times M, and the bottom surface acting on the system. Part B. At the instant you release the block, what is the net force on the block? Express your answer in vectors. So knowing from the momentum principle, the change in momentum equals 0 and F net equals 0 in this system because there is no momentum or movement occurring in the y direction, which is the vertical. So for the spring force of the left spring, it's negative Ks 4 over 3 L0 minus L0 x hat. While for the spring force of the right spring is negative 2 Ks 2/3 L0 minus L0 times negative x hat. This is negative x hat because when the spring is stretched, it is in the negative x direction. So when added these two together, we get F net equals negative Ks L0, comma 0, 0. And the y and the z are 0 because there is no momentum occurring in those positions. Part C. Determine the new velocity of the block a short time delta t after being released. Here delta t should be taken as a given. Your answer must be also in vector form. So knowing Newton's second law, we know that the final velocity equals initial velocity plus the net force over mass times delta t, the change in time. So we're trying to find final velocity in this case. We know that it starts at rest, as stated in the problem, so initial velocity is 0 meters per second. F net, as we found in the previous part B, says it's negative Ks L0, comma 0, 0, and then we know that we can just move delta t over m. So when you multiply delta t over m, we get the vector negative Ks L0 delta t over m, 0, 0, for the final velocity. Part D. Using your answer for part C, calculate the new position of the block. It should also be a vector. So in this, we know the updated position formula, which is final position equals initial position plus v average, which is velocity average, times the change in time. In this case, v average is equivalent to the final velocity, which we found in the previous problem. So knowing that, we know that the initial, as given in the problem, is L0 over 3 when it's at rest, comma 0, 0, along with the v average, which we just found in the previous problem, times delta t. We get the final position as L0 over 3 minus Ks L0 times delta t squared over m, 0, 0. Part E. Determine the new force on the block. So we pretty much just plug in what we just found for the position, which is, in our case, L, which is, we plugged it into part B's equations. So these are the answers for each one of them. And in the end, we get F net equals negative ks L naught plus 3 ks squared L naught delta t squared over m 0, 0. Overall, this problem was not as difficult. It is just that you have to make sure to apply each variable and don't try to skip around and try to fully understand the concept. Thank you.